people ask me, how can they get started with BCIs if they don't have a neuroscientific background? That's a really common question, and to be honest, it was really quite niche to work on BCI startups, BCI projects for people who don't have the background that comes from academia. But that changes now, and there is an amazing opportunity available for everybody to contribute to the state-of-the-art speech decoding and get speech prosthesis that one step closer to the clinic with your contribution. So it happens that the NPTL lab or group at Stanford have published a challenge. They open sourced their most recent, highest performing speech BCI, and they have published a challenge to let us help them optimize the decoder, improve its accuracy. There is a $6,000 prize that can be shared, and in the next 90 minutes, the uCat team plus other people who want to join us have formed a group called LoudMouths. We're going to be discussing publicly details of the competition, details of the paper, and brainstorm ideas for how to make it better. I encourage anybody who has worked with natural language processing, with neural data, with even large language models to come and join us and to apply best practices from the industry to a project that truly matters, a project that can restore expressivity to millions of people around the world who have lost it and have their mind locked away by their own body.
Welcome, everybody. I just want to take the time to say thanks again for joining up. This is like a meetup that we're doing both with the neural data science meetup that Oliver runs. So like shout out to him for also taking the time from his people to put this together as well. And a lot of work, I think, has been going into this from Oliver and Sam to get this project started. So they're going to be primarily like the ones speaking, but I'll also chime in to tell people what they can do and like where they can contribute. And I think that's a very valuable thing, especially this project. For me, it's getting me excited about working on BCI projects again, which is really cool. Okay, so we have a good number of people here. Okay, I think we're going to then start then. All right, I'm going to make you host, and I think you get to present from that.
Hi, everybody. Okay. Right. So I'm assuming people read a little bit of the agenda for the meetup today. So welcome again to the meetup. I'm really glad to be talking about this, and you'll see why. So I'm Sam from the project uCat. That's up right. I'm really going to just spend about 10-15 minutes giving a little bit more perspective about the things that we're going to talk about in this meetup. I'm going to start off with talking about this statement here in particular: mind works, body refuses to. I wonder how many of you guessed what neurological condition this statement refers to. Mind works, body refuses to. Well, it's paralysis. And there is around 363 million people with paralysis, primarily, that prohibits them from engaging in mobility and communication exercises, activities, like you and I are engaging in right now. 100 million people of those need assistive technologies to communicate today. These are known as augmentative and alternative communication. And then 1 million of people alive right now, worldwide, are affected by such severe paralysis that they're unable to move anything but their eyes. This has a special state, or a special term to this state. It's called locked in. And at that levels, you're really forbidden from using your body, even though your mind works, to engage with society, to engage with your loved ones, to participate in activities you used to enjoy, to express yourself. And most people I speak to about paralysis, they really don't think that paralysis is fixable. Like, this is kind of an accepted fact. Like, okay, everybody in the world is going to die at some point. Also, if you have paralysis, it's not something that can be remediable, fixable. And I don't blame them because there really hasn't been any solution for severe paralysis ever available. And that kind of changes. This era of having no solution to paralysis changes very recently with the advent of motor neuroprosthetics, more simply motor BCIs. Here on the picture, you're looking at a brain implant, which is the kind of principal component of a motor BCI, developed by BlackRock Neurotech as the pinnacle of data acquisition tools, where this little array here is a microelectrode array, typically with 100 small electrodes that is implanted into the motor cortex and can decode any motor intents that the participant, the patient, has before the paralysis nullifies them. It is connected through this pedestal, through this cable into the pedestal and then into a decoder server. And very, very recently, this is 2021 until really now 2023, there have been only a few groups who have tried to decode these motor intents of how I'm about to move that are related to speech production. So how am I going to coordinate my mouth, my tongue, my larynx to produce words if I could speak, right? Even though I'm paralyzed in this case. And the state of the art here is that they were able to use this very Utah array brain implant technology to decode speech at very fast rates. So at 62 words a minute in 2023, this is 15 times faster than eye tracking or previous invasive BCI spelling. So the previous modality was relying on using kind of like an imagined movement of the hand and then imagine grasping to select letters from a keyboard one by one. Now, people, as they imagine speaking or as they attempt to speak, that activity, that kind of orchestration of those muscles I was talking about, those articulators, is decoded directly into words. I'll talk about that a little bit later, but 62 words a minute was the benchmark. It's very expressive, not just few words that people can detect with these motor prostheses, but actually they can detect words from a very large vocabulary of 130,000 words. And it's somewhat accurate. It's accurate-ish. These words that are being decoded are decoded at 76% accuracy, which allows people to express themselves quite accurately, but, every fourth word is incorrect. The commercial speech recognition for decoding speech to text is at around 95% accuracy of decoding the right words, so word accuracy rate.
Sorry to interrupt you, Sam. We do have a question really quickly. I would say also, you guys try to put all your questions to the chat if you can, but we also want to make sure we make use of Sam's time as well, because I think he has to leave a little early. So Teresa Oklava, do you have a question?
Oh, yeah, sorry. Next time I'll type it in the chat. Yeah, so I was just wondering, in case where subjects attempt to speak at rates that are faster than the 62 words per minute, does the device drastically decrease in terms of accuracy, or what exactly happens and how was this upper limit determined?
Oh, that's a good question. I think the research here is limited by how the actual modeling architecture could interpret the signals from phonemes. And this is how they would be reconstructing words from a kind of a time series of phonemes with the highest probability, depending on how the words were produced by the participant. But the limit was really set by, in this case, I believe, as how quickly they were able to capture individual phonemes to then be able to apply a language model to produce like a word output out of those individual phonemes. There are ways to speed this up, but I think if you compare it with normal speech, if people able-bodied, it's about half as fast as I talked to you or how fast you were asking the question, which is really not great. It's not as fast as, people can communicate right now, but only this is still already a monumental achievement that can get only better with better decoding approaches, which is kind of where we're meeting here now. Okay, I'll carry on. This is, jump in with questions if they're about what I'm presenting. We'll also use the chat. Chat is good for collecting them and addressing them later. by people who are much smarter than me. But I wanted to outline a little bit more in detail, but still an overview of how they were able to extract these words, right? They were able to extract words from neural activity. So as the participant is looking at the screen has some prompts to them, represented as text. For example, hello. The participant will attempt to say hello, and as they do so, neural activity from premotor cortex, precentral gyrus, is decoded, acquired by those 4 very utile arrays that I was showing earlier. And it's acquired into threshold crossings and spike band power, which is then inputted into an RNN. That's really the workhorse of the most recent speech neuroprosthesis that has these results I was talking about just before here. The RNN outputs a probability of phonemes as time series, but to make it, to transform the phonemes into kind of discrete words, they combine them with a language model to get to the word output, which is then read out loud by a kind of text-to-speech algorithm. I think they just use Google. And what they've done is that they are actually fully acknowledging at the lab that really the main issue here, the communication rate, the information transfer rate is quite good. It's quite fast. It's just not accurate enough. Every 4th word is not accurate enough. And they've asked the community to try and help out. So they've published a challenge competition where you can win a prize pool of $6,000 if you can optimize the decoder the most, right? If you can minimize the word error rate. That's how they are judging the success of the competition on some held out phrases that the participant was repeating, right? And that means that all the data used in this study is open source. The models are open source, available to us, and they're also kind of prepared for machine learning, people who have limited knowledge about computational neuroscience, say. And I would like you to see if you can do something that blows this benchmark out of the park. Make it something that's below 24%, below 10% if possible. And to be honest, speaking with people in the industry, the accuracy of speech decoders is one of the biggest hurdles in making this system, this solution, available for patients with severe paralysis in the clinic.
Hey, Sam, sorry to interrupt, but it looks like Igor's waiting in the waiting room to get in, and I'm guessing there's probably other stragglers as well.
Oh, whoops. I don't know. I'm very new to using Zoom as a host, so we all of a sudden doubled our participant list.
Yeah, sorry about that, guys. But all good. We're still talking about the competition, and Sam is just giving an introduction to how people can contribute, and Oliver will give a talk later about what the paper is all based off of later.
That's it. I just wanted to outline that we are one of the teams that are trying to actually go ahead and optimize the decoder that I was just describing. For anybody who's joining just now, it's decoder able to transform neural data into speech at 62 words a minute over a very large vocabulary at pretty good but not great accuracy. And I would like you to, John, this is a fantastic opportunity. This is the first time I'm personally seeing a data set, that's an invasive data set that's open source and prepared and has a challenge against it as well. That is this cutting edge, right? You're able to get really to this paper that I was talking about, and we'll be talking about more depth here, has been published less than a few months ago, and is still, pinnacle of what this modern neuroprosthetics are about. And I wanted to leave you with one final thought before I hand it off back to Brian and Oliver, which is, is there a possibility to use this down the line? So I'm from the project uCat, and one of the integrations that we work on is to imagine how we can use decoded speech to help patients express themselves again in virtual reality. I want to play you a clip, but I don't think this will actually play, so I've instead just played it from here. So as people are repeating words, This is actually the first demo I recorded just before this call. You're the first ones to see what we have. You can decode the words into the neural activity into words. I don't know if you can hear my voice, but we're substituting that because we don't have neural signals. And then use the voice to select things on the menu. And for instance, now go to a different practice area and practice things like phrases and repeat those phrases. So you can get better at using the speech prosthesis. Once you're able to do that, you can have conversations with people inside the metaverse, conversations with this AI avatar we called uCat. And we're building it so that it's kind of offering people a way to use this decoder or use this data that's being decoded if they're paralyzed to some benefits to them, right? To meet their loved ones in the metaverse, or to draw some things on the board if they want to, or to write things down that they couldn't if they're locked in. That's my final piece of insight, and I hope that made sense. If you have some questions, I'll move into the chat now, try to answer them there. Or I'll just call people out and we can have a discussion. Is that fine, Brian, Oliver?
Yeah, I think it's good. I think we have one question here from, and please apologize if I'm mispronouncing your name. Jay Wick Lin.
Yeah.
Cool. Actually, do you want to ask your question?
Sure, yeah. Is there any specific tools like mathematical techniques that you guys use to get rid of the neural artifacts? I know there's a lot of noise in EEG and ECOG data, and I was just curious what kind of tools are effective in classifying phonemes in particular.
Very good question. I can speak to maybe non-invasive BCI, but I don't think I've never had to deal with like intracortical data. So we typically go through like different kinds of filtering to go through like just denoising like motion artifacts with EEG data. Intracortical data, I'm not so sure. And then there's also other things that you can do depending on like what you're dealing with EEG data, like bad channel replacement as well. You know, there's a lot of work that goes into cleaning out like motion artifacts.
I can speak a little bit to that. So in the case of, something like this, where we're trying to come up with online decoder solutions, basically for intercortical data, the data already starts out much cleaner. But the main thing that we tend to do is first, we're going to do a band pass on the signals. And then what we're going to do is we're going to impose a convolution on some lag that's reasonably small, so that it doesn't interfere with the ability to stream the data. And then finally, we're going to look at threshold crossing. One of the other things that we will sometimes do in order to identify waveforms and how they stand out from noise is that we might use a wavelet. And in that case, what you're going to do is basically convolve the wavelet with the signal, and you're going to get a power spectral signal that really spikes high whenever the a neural waveform seems to appear. One of the nice things about intercortical data is that you do hear individual neurons spiking. And so as a result, it's a lot easier to distinguish noise from signal. One of the big challenges in intercortical data analysis is the sorting out which neurons actually generated a waveform. But for neural coding purposes, especially for online purposes, it turns out that that's often not necessary. And so you're generally not going to be doing spike sorting. Does that clarify your question? Yes.
Very cool. Anybody else have any questions before we go forward? Just first type them in the chat. We'll let you talk.
Yeah. And please, why? So I figured I would maybe introduce myself because I almost answered that question. My name is Sarah. I'm actually a former BlackRock employee and was one of their lead engineers up till about 3 months ago. As you said, intercortical data is pretty clean, very EEG, and I'm really tired right now. I am actually in the UK. Sleep last night. Sorry, I lost my train of thought here. I am really tired. I should go to bed. But I've worked.
It's good to see you again, sir. Good to meet you in the UK.
Yes, I did make it to the UK. I did. And I was on an overnight bus last night, and that was a really bad idea. Really bad idea. But yeah, you don't need to do a lot of filtering because there's not a lot of noise from like EMG or muscles, as it's right there. In terms of spike sorting, though, there's all sorts of open source spike sorting algorithms like Mountain Sort, a couple of others that I can't think of right now. The spacing of the electrodes, though, you do tend to pick up activity from more than one neuron in the neighborhood. But they come and go. And so there are different algorithms we use for that.
Very good. Thanks again, Sarah. I appreciate that. Also, this is a project where I'm also very learning about intracortical EEG like data for the first time. Most of the time, my experience has been with like non-invasive, like neuroimaging. Teresa, you also have a question here. Do you want to ask it?
Yeah, sure. So I was reading the paper, and I noticed that depending on the vocabulary size, the error rates differed quite massively. And I was wondering, what's the conceptual explanation as to why that happens, assuming the noise is constant, irrespectively of the vocabulary size? So why is it that the accuracy decreases so steeply if the vocabulary size expands, assuming the total number of phonemes should stay the same?
So I can speak to that. I think that the main reason is because the decoder that they're using leverages linguistic priors. They're using an n-gram model. And if there are more options or more possibilities, then ambiguities at the representational level can lead to false inferences. So basically, if you have a linguistic prior that this is the most common thing that's going to follow from the previous token, and you have some ambiguity in the embedding, in other words, there are some embeddings that are similar to other embeddings, then the prior might nudge you in the wrong direction. And that's less likely if you have a smaller vocabulary.
Very good. Okay. And so Oliver has a presentation that's going to be happening pretty now, but I would say for any of your questions, can you guys put them in the chat and we'll address them right after Oliver's presentation? Cool. Yeah. All right, Oliver, I'm going to make you host. A second, and then you can go.
All right. Just before Oliver, you go in, I'm going to log off now. It's close to midnight here, and it's my birthday in a couple of minutes, so I need to get ready for that. If you have any more questions that to do with that,
Happy birthday.
Happy birthday.
Thanks, Kara. Thank you. Any questions, you know how to find me. Yeah, uCat, Sam, and I hope you join the team. We get to chat more later.
Yeah, thank you for taking the time so late.
Yeah, appreciate it. All right. Your turn, Oliver.
All right.
So we're basically just going to go through a summary of Willett et al., which is the paper that that inspired the competition. If you don't already have a link to the paper, you can link it here. So we're just going to go through three sort of major sections. The first part I'm going to kind of speed through, but it's just about data acquisition, including the experimental procedures and data collection for those of you who didn't read that part in depth. Then we're going to talk about the pre-processing and training stage. So how the data was processed before the modeling, how the neural RNN decoder works, and how the speech n-gram model works. And then finally, we're going to look at evaluation. And at that point, we're going to discuss very briefly the performance metrics that they achieved. And then we're going to talk about possible elaborations. And I want that to be an interactive discussion. So let's just move through this. The study participant, who has been termed T12, she enrolled in the BrainGate 2 neural interface system clinical trial. She was a left-handed woman, 67 years old, during data collection. She was diagnosed with a condition called bulbar onset amyotrophic lateral sclerosis. Many of you probably know that as ALS, at age 59. And she was implanted with a 64-channel microelectrode array in her left hemisphere. The data were reported from post-implant days, number 27 to 148. She had severe dysphagia due to her bulbar ARS. And basically what that means is that she was unable to speak, even though she was able to express herself to a limited degree with her hands and her face. She communicates primarily through a writing board or an iPad tablet. So the first thing they did in order to identify the correct brain region to implant is they did MRI speech lateralization. So prior to doing any surgery, they did functional bold fMRI imaging, and they asked her to do a variety of speech-related tasks. They found that language was lateralized to the left hemisphere, and so they went ahead and put the implant on the left side of her brain. For those of you who aren't familiar with lateralization, it's actually surprisingly common for people to have an inverted lateralization. So the right brain distinction is not always as straightforward as people think. So the two brain regions that they targeted were 6V, otherwise known as the ventral premotor cortex, and area 44, which is otherwise known as Broca's area. 6V is an area that plays an important role in the planning and execution of motor tasks. And so what they were targeting there was data about the articulation of words. And area 44 is important in speech planning and production. When that area is damaged, people will suffer from a condition called Broca's aphasia, which is characterized by difficulty in forming grammatically correct sentences. So it stores a lot of the information that I think nowadays we might associate with a language model. So it's an interesting target to look at as well. The data collection sessions, neural data were recorded in 2 to 4 hour sessions on scheduled days, typically occurring 2 times per week. During these sessions, T12 sat in an upright position, either in a wheelchair or a powerlift chair. She had used a pillow for support behind her head and neck, and her hands rested on her lap. A computer monitor in front of her displayed cues indicating which sentence to speak or which movement to make. So most of these tasks were cue-oriented. Data were collected in 5 to 10 minute blocks of uninterrupted series of trials. T12 was encouraged to rest between these blocks, and the study reports data from 27 of the better collection sessions. So there were sort of 5 main kinds of blocks or tasks that she underwent. The ones that were of main interest were the sentence speaking blocks, but they also did phoneme tasks where she was prompted to pronounce specific phonemes, as well as single word tasks and orofacial movement sweep tasks. And prior to every sentence speaking block, she did a diagnostic block. So the sentence speaking blocks, basically, during a delay period, the text of a sentence was displayed on the screen above a red square, allowing T12 time to read and prepare to speak. And after that delay, the red square turned green, and T12 attempted to speak the sentence, either aloud or silently mouthing it. Once she was finished speaking, she pressed a button in her lap to move to the next sentence trial. The single phoneme and word tasks were similar, except she was prompted to speak a single phoneme or a word. Each phoneme was cued with both text and an audio sample. Vowels were spoken in isolation and cued with text of a word containing that vowel. And then consonants were paired with each vowel. So essentially the phonemes were composed of consonant vowel pairs like ka. Single word tasks. So T12 also spoke individual words from a 50-word data set from Moses et al., which you can find a reference to here. Each word was cued with text only. For the orofacial movements tasks, basically she was given things like tongue up. The diagnostic block was used to calibrate sentence speaking blocks. So a single diagnostic block was run at the start of each of the speech decoding sessions. What she did there was they set the electrode sessions using linear regression coefficients, and then after they got a baseline, they asked her to speak individual words from a diagnostic set of 7 words that were designed to span the space of articulation. And you can see what those were. So it was ba, choice, day, kite, through, or though, I guess, veto, and were. And apparently those cover all the possible English phonemes. Okay, so I'm not sure if this is really particularly relevant. I did a lot of detail, but basically the tasks were delayed for a period of duration, and they were pseudo-randomly drawn from an exponential distribution. The go period durations were fixed for non-sentence tasks, and for sentence production, she advanced the trial by pressing a button. So in that case, it was interactive. The orofacial movement sweep tasks, a short return phase followed the go period. And you can find more information in the supplementary section of Table 3 in the paper. So after undergoing these tasks, they underwent, or they did like kind of a cycle where they went through training and evaluation sessions. Real-time speech decoding was evaluated in multiple sessions, both for voiced and silent speaking behavior. The evaluation sessions reported on the study were conducted with a final version of the real-time decoder and parameters. Each evaluation session began with a diagnostic block to calculate the threshold, as we discussed. There were these things called open loop blocks of sentences, which were collected without an active decoder. So basically, at the beginning of the study, they were collecting this information without having any decoder running. The decoder was then trained using these blocks in order to obtain stage 1 RNN decoder. And then additional training blocks were collected with real-time feedback, where the decoder output from stage 1 RNN was displayed in real time. So something kind of similar to the way that uCat has developed their interface. The RNN was retrained a second time in order to yield a stage 2 RNN, and then the stage 2 RNN was evaluated on specific sentences from Moses et al. And randomly selected sentences from switchword corpus. So those were sentences that were not included in the training set. The initial training data collection sessions were used sentences from Open Web Text 2 corpus. Subsequent sessions used sentences from the switchboard corpus of telephone conversations. Sentences were then selected based on criteria, including expressing a complete meaning, avoiding confusing or distracting meanings, and ensuring a diverse sample of conversational texts, which is fancy speak for they picked stuff that looked nice. For each evaluation day, 3 evaluation blocks were run, including 1 block of 50 sentences used for the evaluation of Moses et al. 2021, and 2 blocks of 40 sentences, each from Switchboard. And the RNN decoder was never evaluated on a sentence it had been trained on, ensuring every sentence was unique. Let's take a look at questions real quick. Brian, did you see anything that I should respond to now, or maybe we should wait? interactive.
So there is a discussion, I think, that from a question Teresa posed. She mentioned in patients with ALS, do the rates of disease progression differ across brain regions implicated in language processing and production? And then how much intersubject variability is there?
Let's see. Okay. Yeah. I mean, to be honest, I don't really know. My area of expertise is actually Alzheimer's disease. I'm very fascinated by neural coding, and we do a lot of neural coding research at our lab, but it's mostly with rodents. So you'd probably have to just look that up or ask an expert in paralysis. Sam might know, but I think he's gone right now.
It does not affect speech production regions of the brain. It causes a disconnect of the brain from the ability to control motor functions. It does vary in progression rates based on patient. Like the most famous, obviously, would be Stephen Hawking. And because he was diagnosed and had early onset very early in his life, it proceeded relatively slowly, and he lived a very, very long time. That's not typical, though. Usually progression is several years, and the patient succumbs to the disease. Usually because of complications in breathing or swallowing, things like that.
Great. Thank you so much for that insightful response.
Yeah, very much so. And also, I think if somebody does have some sort of like expertise in what we're doing, please feel free to chime in on the chat as well. And then we'll also give you time to speak as well. I appreciate what you did, Sarah, very much.
Absolutely.
Yeah.
All right. So at this point, I would like people to put on their note-taking hat. What we're going to be looking for are red flags or issues and ideas for improvement, as well as green flags or strong points that you feel we should preserve or try to replicate regarding how they approach the decoding task. Remember, this is interactive. We're entering a competition and also just more generally trying to learn about and improve these models. So the idea here is to sort of pay skeptical attention to what it is that they did and think about your own knowledge and come up with some ideas, which we'll discuss after we finish this section. So for neural signal collection and processing, basically they recorded the neural signals from the microelectrode arrays that were from the Neuroplex E system from BlackRock. The signals were analog, filtered, and digitized at 30 kilohertz, and they were processed using custom software in the Simulink for digital filtering and feature extraction. I believe that just means that they used a MATLAB package. Digital filtering began with a high-pass filter with a 300 hertz cutoff applied non-causally to each electrode. So non-causally means that they applied it without considering anything after the time point under consideration, or the most recent time point. Linear regression referencing was applied to further reduce ambient noise artifacts. So this is what they did during the calibration phase. And then bin threshold crossing counts at 20 milliseconds were computed by counting the number of times that the filtered voltage time series crossed the amplitude threshold. As we'll see later, 20 milliseconds actually has an interesting significance. Threshold crossing rates and spike band power were commonly used measurements for local spiking activity. So basically, this is what everybody does. There's really not much room for improvement in this particular area. So the feature pre-processing and day-specific input layers. So threshold crossing rates and spike band power features were pre-processed by binning into 20 millisecond time steps, and the features were z-scored. Meaning that they normalized them by subtracting the mean and divided by the standard deviation. They were causally smoothed by convolving with a Gaussian kernel with a standard deviation of 40 milliseconds that was delayed by 160 milliseconds. The features were concatenated into a 256 by 1 vector, and then transformed using day-specific input layers. So that's kind of an interesting thing. Because of non-stationarity or variance across days in representation, they decided to have a different input layer for every day that they used the decoder. Z-scoring was performed using block-specific means and standard deviations. So in other words, they were recomputing the Z-score kind of in a moving way. And for the offline stuff, what they did is they just used the whole block. The day-specific input layers consisted of an affine transformation applied to the feature vector, followed by a soft sign activation function. In other words, they were doing the linear regression. And during training, dropout was applied both prior and after soft sign. For the online training, they had something called a rolling Z-score. So basically, during each online evaluation, a rolling estimate of the mean and standard deviation of each feature was used for Z-scoring. And for the first 10 sentences of a new block, a weighted average of the prior block's mean estimate and mean of the current block sentence was used. So in other words, at the beginning of a new block, they used the previous block estimate, and they just took a weighted average that leaned further in favor of the current block as time went on. And then at a certain point, they shifted to just looking at the current block once the sample size was large enough. After 10 sentences, the mean across most recent sentences was used, and the standard deviation was updated in the same manner as the mean. So the neural phoneme decoder, the study utilized a recurrent neural network decoder to emit probabilities of each phoneme. In other words, a big vector of probabilities for all the phonemes being spoken. And they did that every 80 milliseconds or over the course of 4 bins time sweeps. These phoneme probabilities were combined with a language model to deduce the most probable sequence of words, considering both the phoneme probabilities and the statistics of the English language. Training data was recorded at the start of each RNN performance evaluation day, where the participant attempted to speak 260 to 480 sentences at their own pace. These sentences were randomly chosen from the switchboard corpus, as we discussed previously. The RNN was trained on this data combined with data from previous days. In other words, they did transfer learning. They just kept training it. The unique input layers were used for each day to account for day-to-day changes in neural activity. Rolling feature adaptation was employed to account for within-day changes. By the final day, the training data set consisted of 10,850 total sentences, and the data collection and RNN training took an average of 140 minutes per day. So quite a lot for one person. Inference with the N-gram language model. So the study used a language model decoder implementation called WeNet for real-time inference. And WeNet is essentially a wrapper around a package called Caldi, and it simplifies the implementation of real-time decoders. The decoder runs an approximate verbiti search or beam search algorithm on the word search graph that they had constructed. This graph encodes a mapping from sequences of connectionist temporal classification labels emitted by the RNN to a sequence of words. On the next slide, I'll have a little bit more detail about that. During inference, the beam search combines information from the word first search graph and the RNN decoder about the CTC labels, which are likely occurring at each moment. And the decoding parameter for beam search are decoded in table 6. So you can actually take a look at how these parameters looked. The beam search runs every 80 milliseconds after the RNN emits CTC label probabilities, and each beam search step took less than 1 millisecond to complete on average. So connectionist temporal classification loss is an interesting approach to dealing with the fact that you have this continuous time series that you're trying to relate to unaligned data. CTC is used for training sequence models where the timing of the output labels is not aligned with the input data. CTC can combine sequence priors from language with the data, and CTC assumes a many-to-one relationship among tokens from the input time series and the label. So like in audio processing, the standard bin width is 20 milliseconds, which I believe is why they just adopted the same bin width here. And CTC maps the 20 millisecond bins to repetitive token sequence, including pauses, which are then mapped into non-redundant final output. So an example of this would be, let's say you have a sound and you break down that sound into predictions about phonemes. So in this case, you've got ba, ba, and then and then tu, tu, tu. You're like, okay, well, that's bat, right? That spells out bat. Or at least that's the most likely, reduction of the mapping. There's a nice little sort of parsimonious description that I found very helpful, linked here in this QR code. So if anybody wants to kind of take a closer look at how that algorithm works, they should just maybe take a photo of that link right now. Basically, CTC loss sums over all the likelihoods of all possible ordered sequence, but they do so using dynamic programming, so it ends up being an n-squared algorithm, which is not too bad, all things considered. And if you want more details, or maybe later for reference during our discussion, maybe just pull that link up. So the offline language model optimization, after data collection, further optimization and LM revealed that online decoding could have improved by up to 6.4% with enhanced architectures. In other words, the 5-gram model that they used. To improve the linear model, a 5-gram linear model language model was used instead of the 3-gram model, and a 2-pass coding strategy was employed. So the first pass outputs a word lattice and an efficient representation to encode possible word sequences, and then the second pass uses an unpruned n-gram language model to rescore the word lattice. So basically they did autocorrect, right? So they created a sequence of predictions, and then on a second pass, they went back and they looked at the larger context, and they corrected things that they could using a bigger word history, right? So remember the initial pass, what they're doing is they're only looking at very short sequences of phonemes. And so there isn't that much linguistic context. And in the second pass, what they're doing is they're introducing linguistic context in there, in like a more conventional language model approach. Additionally, a transformer LM was used to rescore the candidate sentences in a third pass, and the transformer language model can model much longer contexts. The study used the publicly available pre-trained OPT language model, which was used to rescore the n-best outputs from the 2-pass decoder. So essentially, they layered on multiple ways of introducing additional linguistic context and priors. So I hope people were taking notes. I know I moved kind of fast. Maybe do people want to take a minute to kind of think it over, or do people want me to go back to any slides before we move on to the discussion?
Yeah, I would say also, please feel free to in the chat to let us know too. That makes things more direct. I mean, one of the other things we do have some questions too. I think one, we can probably just go over this now. There are a couple here.
Okay, why don't we discuss what seems relevant?
Sure. I think they had a general question, but it's Jaywick Lin, I think, asked, is the assumption of targeting Broca's area that initially distributed representation of meaning becomes localized in Broca's area?
Kind of, yeah. I mean, it's an area of interest because it's responsible for helping to generate sequences. And to be honest, I mean, I think what they actually found was that 6V was where most of the interesting information was, given the approach that they took. And we'll get into this, I think, more of the discussion. I have a few sort of like starter suggestions and criticisms that we can build off of. And one of them includes some considerations of the fact that the way that they decided to approach the problem may not have taken advantage of the kind of information available in Broca's region as much as they could have.
Understood. Okay. Then another question by Claire Gu is it possible to collect a data set as big as LibreSpeech where you get 1,000 hours?
Where we get what?
1,000 hours of speech data. So like LibreSpeech, I guess, contains 1,000 hours. So is it possible to get a data set that we have as big as something like 1,000 hours to use?
I would imagine that that would be something that might happen in a clinical trial across a lot of subjects. When it comes to something more non-invasive like EEG, I have no doubt that you could do 1,000 hours, right?
Sure.
I mean, you could literally just have one person sit there and listen to a bunch of audiobooks and
it's true. I mean, like I came from a company where we did long-term recordings because we had an earbud as the form of our EEG device, right? Which we got like 48-hour recordings at a time from people who were sleeping.
Yeah.
So comfort's a big thing, I think, to that challenge. So I think nowadays you can see more of that.
Yeah.
Yeah, okay. And then another one here by Teresa. I think she maybe said never mind, but she asked, how is this model different from traditional large language models?
Yeah.
Yeah.
Yeah, I mean, I think that some of the slides clarified that.
Teresa, you want to go ahead?
Yeah, so then the later slides largely clarified my confusion, but I'm not really familiar with LLMs outside the context of like traditional language models that deal mostly with the semantic content of languages. And I was wondering to what extent approaches that are, so for example, 4 days ago, Anthropic published this paper where they basically conjectured that, for example, polysemanticity appears to be possible even in the absence of superposition. And they were showcasing how feature splitting may occur with larger data sizes. And I was wondering, somewhat abstractly, and I don't really know how these things really work, but to what extent are advances in large language models that don't deal with phonological properties of language at all translatable to such settings to improve the accuracy? I've never really worked with LLMs outside the traditional ones, so maybe this question is not even the right type of question, and I'm just like fundamentally
No,
confused.
you're absolutely on point, actually. I mean, the emergence of LLMs is revolutionizing the decoding performance for neural data. There was actually just recently, there was a paper that used a contrastive learning approach in conjunction with an LLM in order to get surprisingly good decoding accuracy from EEG. They were able to get like between 40 and 80%, depending on the session, which isn't great for like actual use, but it's incredible because previously people weren't able to get more than like 2, maybe 3 distinctions out of EEG reliably. And I think the upper bound was like 10 for something that was usable. So it's a huge leap forward. And basically the way that ends up working is that these large language models, you can kind of think of them as like maximum likelihood estimators for like incredibly complicated high dimensional spaces of possibilities, right? And if you can guide something along the manifold of possibilities without it getting outside of that manifold, you drastically reduce the space of possibilities for the direct decoder to deal with, right? Mm-hmm. And that's like what they were doing, for example. They kind of took like a multi-model approach, but they were leveraging the power of conventional language models in order to basically go back and kind of like increase the plausibility of the time steps. And, you know, one of the interesting possibilities here is that maybe we can start with a pre-trained model, something, you know, decently large that has a lot of information about the structure of like the English language. and use that to get it to converge by sort of helping it to understand the patterns that you might expect from within the neural data set, right? Which also follows similar statistical rules because they are in fact encoding language. The trick is to just get that mapping right. So I don't know if any of you guys are familiar with like abstract algebra, but essentially when you have a large language model that encodes all of this information, what you have is like a category, right? It shows all the transition probabilities given context. And when you have another modality, what you can try and do is you can try and induce something called a natural transformation, which is essentially a structure-preserving transformation between the two things. So what that means in kind of simpler language is that you've got this one sort of complicated, beautiful structure of probabilities conditioned on priors of many, many different kinds. And you have this other data set that you know has kind of a mirror image or a reflection of that in there somewhere. And now that you have this first one with all of its intrinsic structure, it's a lot easier to solve the problem of figuring out how to induce the same intrinsic structure onto a model of the second data set. Does that kind of make sense, or am I kind of losing people here?
No, I think you're making. Go ahead. Sorry about that.
Yeah, so I think it makes sense, but I still have a few points I'm not entirely sure if I understand correctly. But so, for instance, my understanding of how so in the paper that I'm referring to, which dealt with like a one-layer transformer that was fed very large data sets, they were using dictionary learning, which is basically an autoencoder, where they try to show that it can find an overcomplete basis, and because it fundamentally needs to compress higher dimensional data into lower dimensional space. And previously in the mechanistic interpretability field of research, people hypothesized that superposition, whereby different neurons represent different features simultaneously, arise by necessity, given that there's a higher number of features than there is a number of neurons. But when they try to control for this using things like one hit, some term where they basically only activate one neuron, so at least in principle, it should be possible to induce monosemanticity. Polysemanticity remains preserved across neurons, which then implies that these apparent ambiguities where a neuron represents multiple features simultaneously, even though it could in principle have more sparse representations dedicated to one feature at a time, still is optimal to minimize the loss that the dictionary is learning. And the reason I'm bringing this up, even though it seems somewhat tangential, is that I'm really not sure to what extent there exists a one-to-one correspondence between the phonological data and like how it maps onto the language stuff, because I'm not really sure if it is the case that just like there can be vectors made out of the meanings of words and whatnot, so that we can do the same thing with the phonological data, so that the outputs of the existing large language models that have been used for speech decoding could be used as the inputs to further LLMs that have never been trained on phonological data, and whether these things could be compatible. And moreover, one thing I'm not.
I got to stop you right there because I'm starting to lose track of the points that you were making. So if I remember correctly, the first point that you were talking about has to do with sparsity versus degeneracy in neural representation, and that's like a big topic in neural coding, right? Like that's still an open debate. Last year at Cosine, I don't know if you went to the Cosine conference last year, but there was a whole like track at the follow-up workshop session, where pretty much it was just dueling presentations debating that issue. So all I can say about that, like in this context, is that it's an open problem. Most likely, there's neural degeneracy, and sometimes when sparsity is advantageous, it makes sense to create a more sort of sparse representation in the brain. nobody really fully understands how neurons learn either, right?
Yeah, so like this kind of reminds me of the stuff that I actually studied when I was doing neuroscience research. So we looked at neural representations of infants and younger children, and I think that tends to be more of a thing you'll see more in neuroscience literature now because people are interested in how we acquire language. But I don't think you'll see a lot of newer papers for adults in that sense. Yeah.
And so to your second point, though, regarding being able to create these mappings, you're absolutely right. There is a major concern, and that is that neural representations may not be stable. They're subject to drift. And that's actually why they had to create a separate input layer for every single day that they trained. Because I assume they tried another approach and it didn't work because of that change in representation. Obviously, there is kind of a mystery as to how representations remain stable globally, because they do, right? I mean, as human beings, from day to day, we are able to process information and speak the same language and do the same things. So somewhere in our brain, we're preserving something. But when you just have a teeny tiny little window into the neural activity in the form of just like a little implant at just one layer in the cortex, it's most likely that what we're observing is sort of this manifold drift, right? That's just kind of, we're seeing non-stationarity essentially because of the fact that like, we're just seeing this little window, right? And it's moving around, and there's some stable core to that, but that stable core isn't observable at the scale that we're looking at. In the same way that like if you were to just observe a tiny patch of skin over the course of a year, you'd see all the cells being replaced and everything would be kind of shifting and changing. And there might even be changes that are global, right? That completely look different from how the skin looked previously. So obviously in the brain, it moves faster and it varies from day to day. But it is an open question, right? It's possible that there is an underlying stable latent structure even within that small window. And it's possible that there just isn't. And that's something that maybe we can address with some of our, learning approaches.
Very nice. So Claire Gu has a question about just data. So if the data collection is so low cost and simple, is there any work done using self-supervised training to create a pre-trained model and using transfer fine-tuning on specific pattern patients? I think Oliver said something, but I probably missed it.
So it's really not low cost at all. Implanting a human being with a neural implant is a tremendously dangerous, risky procedure. It's only done when the benefits to that person's life far outweigh the risks. Yeah. And that's a very rare situation. I think I'm sorry, go ahead.
Well, the other thing, what also attracted me to this project is you don't see a lot of their data very open source as well. And like many of the times when I've seen people do studies with like intracranial implants and also like ECOG devices, it's usually with people who already have them because the cost of doing this is like very prohibitive.
Yeah.
Yeah.
So, let's move into the discussion phase. I'm not sure if this is particularly interesting. Let's briefly take a look at the model performance. So basically, there was a 9.1% word error rate when they had the limited 50-word vocabulary, and then that went up to 11.2 for silent articulation. So apparently attempting to actually get those signals through the motor cortex and into her throat, even though they didn't translate, actually was able to improve the performance to some degree. And then there was a 23.8% word error rate for the 125,000 word vocabulary across all of the vocalization days. The RNN often decoded sensible sequences of phonemes before language model was applied. You can see some examples of that in the paper. Phoneme error rate was computed on the raw RNN output, and that was 19.7% for vocal speech and 20.9% for silent speech. And In the competition, they were able to get 15.43% error with the 3-gram model and 11.06% error with the 5-gram model. So this is after doing additional passes with those language models to sort of autocorrect obvious mistakes. And just for reference, commercially viable models will need to achieve less than 5% error rate. And that's ideally what we're shooting for, because we want to make this available to people if we can. So I'm going to ask people to share their flags now. So if you can go ahead and go to this link and fill out the form. I would love it if people could write down some of the stuff that they observed. We can also kind of jump right into it, and I can type as we go since we only have about 17 people. One more question on LLM. In textual prompts, all tokens, let me move that so it's not obscuring.
So one question on in textual prompts, this is from Teresa, all tokens get processed in parallel. Is that also the case with the processing of time-dependent phonological data by language models?
Yeah, that's a good question. I haven't gotten as in-depth as I would like, so maybe we'll have to take a closer look at the paper to answer that question. But I think ideally what they're looking for is a model that can decode online. And so I believe that the performance that they're going for in the competition is actually capable of being online decoded.
Yeah, that's interesting. So I think one of the things I'm also curious about is how most probabilistic models are kind of hard to serve online too these days. Like, so there's from an engineering standpoint, I'd be curious about that.
Yeah.
Very cool. Any info on the CTC law? Okay, we have another question from Michael Meneses. I'm sorry about Michelle.
Oh, hi, Michael.
Or Michelle.
We've worked together before. He's awesome.
Hi, everyone. Hey, Oliver.
I'm sorry about mispronouncing your name. It's Michelle?
For sure.
Is it? Okay. So did the author provide any info on the CTC loss convergence when training the decoder?
Yeah, so the CTC loss, I had a link in there. Later on, I'm going to give you guys a link to a copy of this presentation. So if you didn't get a chance to look at it now, you can go back in the slides afterwards and you can take a look.
Yeah, I'll also email the group, at least in our meetup, like just the copy of the slides as well.
Okay.
Yeah. Also, yeah, another thing that I haven't seen is I think we were talking about this in the group earlier, like in our project. Their weights, their model weights aren't published online. So I think we'll just raise an issue on their GitHub about it so people can see more. Okay, so I guess
I'm waiting for submissions. Have people submitted responses to the form that I sent out?
I actually have to go on there too.
Okay, cool. I just figure it's easier if people write stuff down. Is there a recommended number of members per team? I mean, basically, we're recruiting. We've got 5 people already that are committed to working on this with us. And depending on the size of the pool of people that we recruit and the level of commitment that people want to have, we will potentially break up into teams. I'll get into more depth about the specific kind of 4 categories of contributions that we can make and we can discuss a little bit more about that. But all I can say right now is that it'll depend heavily on how many people want to do this.
Yeah, and then also I put the link in the chat too if anybody wants to fill that out. Yeah, I think what we're more curious about is sort of like different approaches, the way people approach. There's a lot of different parts of this project, right? There's, replicating their results to doing improved machine learning model on both kinds of decoders because they have different sets of problems, to, making things more replicable for people, and then making sure that something is engine, like, from there, if anybody's taking a chance to look at their initial GitHub repo, I can, even from like a software engineering perspective, can see many different ways you could actually improve the project, right? And like,
yeah, totally,
and make it more easily accessible for people to use, like, and probably narrowing down like some of the languages that are used, right? So I think that there's definitely room for improvement. Yeah. I don't know if, Oliver, are you able to see on your end, this kind of like responses you're getting from the...
Yep. Yeah, I've got one so far.
Okay.
Hopefully we'll get, if most people hopefully will respond. Looks like we're getting dropout, but that's good. That means that people are deciding whether they want to think and write or if they just want to disappear.
No, I mean, I encourage, like, even if you want to do this on your own, you can definitely take the reins and do that. I think that's
yes, absolutely.
Yeah. Like there's, let me see here. Oh, okay. There's one. Yeah. The other co-organizer I have for a meetup is like, I think is joining just now too. I think she's coming a little late, but I think she'll want to know more.
Nice. Oh, admit. Yeah. There we go.
Mm-hmm. Okay. So the other parts, I think, Oliver, do you have more to go with the presentation, or?
Yes, I mean, yeah, I've got some starter suggestions of criticisms and green flags, and what I'm kind of hoping is that people will share some stuff. I want to sort of refrain from introducing ideas until we've gotten people's ideas, because generally it inhibits people's creativity if we start converging on things before we've sort of allowed people to come up with their own ideas. If people are not planning on submitting an answer to the form, I guess that's okay, but just maybe let me know in the chat so that I know not to be waiting for you.
Yeah, no problem. Okay, cool.
Absolutely. Yeah, I know it's a lot. Like I'm like asking you guys to just kind of jump right in and start making suggestions after seeing this possibly for the first time, depending on whether you read the paper. I'm liking the suggestions I'm getting so far, though.
The paper link. Okay. I think I could probably just post it in the chat for you guys.
Yeah, that'd be great.
Yeah.
But also, I mean, right now, like the ideas are pretty much just like based on what you've seen so far. We'll have plenty of time to discuss this in more depth and also have follow-up meetings for people who want to participate. I'm just trying to get kind of a discussion going, and I just want to make sure that people are kind of thinking on their own first about this before we sort of jump in and kind of come to some group decisions about ideas and what we think. And yes, absolutely, you can resubmit as many times as you want.
Yeah, this is kind of interesting. Most of like I've done Kaggle competitions before, and like sometimes there's like a very good positive, like, I mean, most of the time people just go for the money, I think, but I think a lot of the time, like the end benefit it's not always like the greatest thing in the world. It's like beneficial to people, but this is like where I think the benefit just outweighs like whatever money people are throwing at this. So it's good.
Yeah, it's pretty cool. It feels good to be able to do something so nice for a group of people that have so many struggles.
Yeah, I think so. And like most of BCI stuff is like usually related to like controlling other things that are not like usually around like people controlling remote devices or like a prosthetic, for example, a physical prosthetic on their body, right? That I typically like get involved with. But this is a little different. Like I actually come from like speech and language research, and like I've never seen anything like this usually, like done in this way.
It is kind of an interesting. To be honest, I think the closest analogy to what they're doing is like sound, like audio speech reconstruction, like the RNN, the CCT loss. All of that is very much in line with sound processing, but then they kind of go this extra step of like sort of going back and reimposing linguistic priors using large language models, which I imagine people working on regular speech decoders are also kind of thinking of using.
Well, even for like even like audio, like machine learning work, right? There's a lot of frameworks that I've seen that people come up with. Like there's the PyTorch based like speech brain project that like a lot of different companies chimed in for, and are getting things like speech to text or text to speech like very out there in the open for people to use. But I don't see people have it from this angle, which is like really cool. Like
yeah,
very cool.
Okay, I don't want to bore people by waiting. Are people still working on the forum, or how are we feeling about that? I've got 4 responses so far. I also don't want to pressure anybody if you want to keep working on it.
Yeah, I think you can fill, like, I think at this point, if you want to fill it out later, that's fine. You can just like go forward.
Okay. Yeah, and honestly, I mean, you can keep adding ideas while I go through this, because I'm going to give you some starter thoughts as well, which might be helpful. Let's see.
Yeah, I think for our meetup too, we're going to have like maybe a starter GitLab page for people to like try and do this on their own. I think I haven't done that, but maybe it would be something we do after this meetup where, you know, we're working right now on sort of coming up with an environment people can use as a starter environment to reproduce things. So it'll be there.
Yeah. Mm-hmm. So some of the strong points that I had come up with were just that the CTC loss is a sound approach to the challenge. And decoding at the phoneme level is theoretically sound for V6. Preprocessing is in line with standard practices for online decoding in general. And the data set itself is pretty amazing.
Oliver, one thing. Can you admit the person who's like in the waiting room for us? I think she's also.
Oh, yes.
Sorry about that.
How do I admit all? There we go.
There you go.
Okay. Let me exit presentation mode. I was thinking I want to start kind of adding stuff to the slides while we discuss. So let me just pull this up. Let's see. So I'm going to try to summarize some of the additional ideas that people had as well. I'm going to start with the green flags.
Regina, if you're listening, so we went through a presentation of through Sam, and also Oliver is giving a presentation on just the summary of the paper and just like how to get started. So if you're listening,
great.
That's what we're doing.
Yeah. Apologies for being late. Hi, everybody.
No worries. Regina is the other co-organizer for the New York City Brain Computer Interface Meetup. So just
shout out. That's later. Awesome.
Yeah.
Hello.
Good to connect.
All right, cool.
All right. So, wow, lots of stuff. So one, let me. So these are the red flags. Let me do the green flags now. I'm just dropping your guys's feedback into ChatGPT and asking it to make bullet points so that we have them for viewing.
I'm curious, like actually what Teresa was talking about. Has anybody ever Llama 2? Like Llama 2 is like something that we could probably try out with something like this because they actually open sourced it, right?
Yeah, that definitely feels accurate. That feels like something that would be very nice.
Really?
Okay, so this was the user feedback.
Okay.
I'm not sure what happened here. Yeah, I think if I just shrink the size of these bullet points, it should. So this is what people were saying. So the RNN's model compatibility, just amazement at how the RNN model could achieve given the context, which makes sense. I mean, most people don't think of RNNs as being particularly state-of-the-art. Utilizing large language models, so appreciation for that use of the large language models, data collection and preprocessing. The approaches to data collection and preprocessing appear to be standard and well executed. Incorporation of a language model, people like that. And overall compelling nature of the project. So here are some starter points. I don't know if people can see. I'm trying to zoom in here. Does anyone know how to zoom in without? Oh, there we go. Okay. So here are some of the main issues that I identified, and then I'll sort of go through what you guys identified, which I'm sure there'll be some overlap. So the first one is representational drift. It was a big red flag for me that the neural decoder had to add new layers for every new day. And I think that's an interesting open problem. Then another one is representational overlap. So in the paper, it was observed that similar phonemes had similar representations, and this could lead to decoding ambiguity. I have a feeling one opportunity for improvement would be to separate those embeddings more. Another point of criticism that I came up with was area 44 represents semantics rather than motor signals, or maybe semantics is the wrong word, but like sequential relations among words. And it seems as though what it is getting at is something that requires a bigger context, right? It seems like it's representing stuff that has more to do with planning whole sentences out in the same way that like a language model is able to sort of plan out sentences. And so maybe a different sampling approach would be appropriate for looking at area 44. And then a couple of other criticisms, which I saw other people mention a lot, was the n-gram model is dated. Maybe the RNNs can be replaced by transformers or convolutional layers, and maybe representation learning can enhance things. So some possibilities would be like variational autoencoders, Cindy sparse learning, autoencoders, contrastive learning, etc. One of the other criticisms that people came up with, which I think is totally valid, is oh wow, that's annoying. The fact that they separated these models. It's kind of kludgy, right? So I believe let me take a look at who actually gave this feedback. I think it was.
Sorry.
Yes, yeah.
Yeah, I can finally talk. Yeah, great. So I'm going to explain what I mean. So this project for me is absolutely exciting because I work on speech, and just in the recent years, we saw so many good works that come into play. One of the example would be Whisper, as a lot of people will know, and also the Wave2Vec 2.0, which also has a pretty amazing and standard, if you will, representation learning, and that actually incorporated the contrastive learning, self-supervised mask prediction, if you will. So I do see a huge opportunity over here to be able to port over these knowledge that we have practiced and seeing success for in other areas, especially in speech areas, very adjacent and related field. In here, you can hear I'm actually really excited to be here. Yeah. So
yeah, it's very exciting.
That's my take. So these models, none of them have a traditional separate AM and LM. They're trying to blend all of these together, especially with Whisper. You can see it's completely one piece. With Devec, the whole learning is one piece, but one could like separate out their linear decoder, which is kind of also trained with CTC loss. And you can also mount separate language models on top, but the whole thing is pretty much trained end to end. And I do see like there could be something super interesting over there to learn things as a whole piece rather than, piece these things together, because each, it's like a waterfall. Each cut of the waterfall, you miss something, by like possible doing quantization, between the different layers of model or things like that. So yeah, this is.
Yeah, I totally agree. I think that's a big, important point, when it comes to designing, an alternative model, is that there really are a lot of very modern, very sophisticated models that do end-to-end decoding. And, it seems very kludgy to sort of have so many layers of things. So I would really love to, discuss more about that. I don't know if there's too many people to have just like an open discussion. Do people feel like we should do breakout rooms or have just like one big open discussion?
I think this is just amount. Like, for one, if people want to talk, put it in the chat first, the question, what you want to talk about, and then we'll put you up first to talk. And sorry again, I feel like if you felt like we didn't let you speak before, I apologize for that. We were just trying to get through presentations, so now it's kind of more like an open forum sort of thing.
Yeah, I think a huge amount of improvements can be made just by reducing the time it takes to process these signals, because it's known that neural data processing is very time sensitive, and just the entire pipeline could have, I don't know, maybe a few milliseconds of faster speed just by figuring out. I mean, we can just tweak the code a little bit, do the same things, but yeah, I don't know how exactly I would do that right now, but that was just the first idea that I had.
So your idea was to improve the pre-processing steps in order to improve the performance of the overall model?
Yes. Do you think it's feasible given the current standardized processes that you guys use?
That's a good question. I guess I'm wondering, because you're right. I mean, you're right that the speed is a little bit slow. Currently, what they're doing is they're looking at 20 millisecond segments, and then they're updating and going back and looking at, further context.
I think also keep in mind that, like, I think the large part of their data is sort of cleaned up and ready for us to use. But like, I think what they're ultimately focusing on for the competition is like word error rate, like decrease, right? So like, I think whatever choices we're making in pre-processing, like we would have to like make sure that we take those efforts to know that like it'll affect word error rate, like improvement in that sense.
Yeah, I think that's accurate. Yeah.
But if you were to decrease time, it would still have to maintain the same amount of accuracy to be useful.
Yeah. I mean, I think the other thing is that, for the competition, they've created this nice, clean, data set for us. And, I mean, we could do additional feature extraction, or we could actually go back into the original data, which they do provide. But at least for the purposes of the competition, they're kind of just saying to everyone, like, please just accept the pre-processing steps that we did. And I think it does make sense because, they did pretty much what everybody would do in the same situation. I'm not really sure what else we could do. I suppose the only major change that I could think of based on my knowledge, like, of implant electrophysiology, is that we might go back and actually retain the waveforms rather than merely having spike counts. Because most of the spike counts are 1. However, there are some cases where there's more than one threshold crossing within the 20 millisecond window. And in those cases, you're going to have a situation where you might have, some representation issues when it comes to actually how to represent that data.
Mm-hmm. Go ahead.
Yeah. I also think, like, there is definitely something to be said to the idea of, like, directly decoding from the raw data. It would be much more computationally intensive, but there is evidence that you can get better decoding performance from the raw data than you can from, like a spike train, like an unsorted spike train like this one.
That's true. I mean, I think one of the things, the idea, I don't know if anybody's used, there's a certain framework I use for time series data now called TS Fresh, but, like, it's meant for large distributed time series that makes, like, all possible features for a time series available for somebody to use. And, like, it's not features you essentially would have to manually code up, per se. So, like, taking a look at that, like, would be very useful for something like that.
So, do people have specific suggestions that are already kind of, like, burning in their minds right now? Like, ideas for improving the model? I love the idea of trying to find a unified model. I definitely agree with that one.
Okay. I mean, also another thing, what do you guys, I guess I'm more concerned with, like, where do you think we can go wrong? I think with something like this. And also, like, with machine learning, I think how being wrong affects, like, what we can do for this. So, like, the effects of being wrong in this sense is, like, somebody would never be understood properly, right? And, like, that's something, like, somebody who's locked in would just have being trouble understood regardless, even though they kind of go through this now, like, applying a machine learning model that we, like, say is right, for example, and generating effects or words that we believe to be correct, and having them be wrong is, like, very, very, like, discouraging, right? So that's the other part of this that I think we have to, like, keep in mind. I guess that's more of, like, a free thought that I guess.
Hey, Brian, I have a comment on that. Let me think for a second. So I missed most of what happened today. Again, I'm apologizing to everyone. But there was a there was a presentation from UCSF, and they have exactly what you were just mentioning. They have a machine learning method for people with locked-in syndrome, and they had a video. The first woman has been tested with this. So she had an indwelling prosthetic, but they also had a device that sat on the bones of her face, and it was electrophysiologically connected. So actually they said the bones, but now that I'm talking, it had to be the muscles. And they told her to not only think of what she wanted to say, but to move her lips, which she could do. She was locked in from the C1 down. And what they were saying is they were using the muscle activations in addition to what they were collecting from the indwelling prosthetic, and they were putting it together and creating what they thought her speech was, recreating what her thoughts were, and they were claiming over 99% accuracy. And of course, they had a very heartwarming video of the woman and her husband. They're crying and they're communicating for the first time. That was the public relations part. But the point was that it was a very effective way of using machine learning. And because it was for the general public, they didn't say what the underlying methodology was and what they were using, but I would suggest to look it up, right? If anyone here is interested in that, because it sounds like that was part of what you guys were talking about today, that I'm sure that UCSF and that group published a paper. I don't remember the name, but it's a recent video on YouTube, and I think if you just put the keywords into YouTube, it'll pull up as a 5-minute video, and then you can look for the name of the group leader. And I thought it was very effective and very impressive.
That's awesome.
Definitely check it out.